we've had it here for about the last 3 years already through an NSF grant. Our speaker today on this technique, low energy electron spectroscopy, as I mentioned before, is Professor Hidde Brongersma, who's from the Department of Applied Physics at Eindhoven University. He received his PhD in Leiden University. He worked many years at Philips Electronics out that way. He's in the middle of a long and illustrious career, just in the middle of it, because he's still extremely active in so many things that he's doing. Among the work he's done, well, his work, he had a leader of a large group of physics and surface interfaces at Eindhoven, group leader of an institute of catalysis, has written and published over 220 papers and 2 review books, and it's just a great honor to have him here to speak to us about the technique of low energy ion spectroscopy and what it can do for us. So without further ado, I welcome Professor Brongersma.
Thank you very much, Henry, for the kind introduction. It's fun to be here again and to talk about LEIS, low energy ion scattering, which is especially known as a tool to look at the real, what we call the real surface, the outermost atomic layer. That is the place, if you do chemistry, that is where reactions takes place. And so it's fun to be able to analyze that, and I'll show you what is new in the field. I'll first give you a general, to make everyone aware how does the technique work, give you an introduction, some applications in the beginning. Let me see how it works. Yes, imaging, nanoparticles, segregation, surface modification, all kind of things like that. What is special about oxides? What is that outer layer? And a lot of people do not always fully understand how that is very different than what you probably think the outer layer of oxides is. Do something on fuel cells, membranes, growth, just how far we get. The principle of ion scattering. In ion scattering, you bounce off ions, so you make ions like helium. Oops, that's something. Let's see how that works. You take noble gas ions like helium, neon, argon, or krypton, depending on the mass resolution you need. If you want a better mass resolution, you will take a heavier ion. You scatter them, say, at a few kiloelectron volt from the surface, and it's just basically a billiard ball game. It's classical mechanics. You transfer momentum to the atom in the surface, and so you measure the same ion coming in and out. So if it's helium in, it's the same helium coming out, and it has lost a certain amount of energy depending on it depends on the final energy depends on the mass of the atom it collided with. So in this particular case here on the right, you see something like neon scattering from an alloy, and you come in with 3 keV, you get an energy spectrum, and that is a mass spectrum of the atoms in the outermost atomic layer. The lateral resolution, it's getting better nowadays. It's not fantastic, not like an electron microscope, for instance. And it is a quantitative tool, and I'll show you some examples of that. One example to understand how it works, take a sample of tungsten, just pure metal tungsten, and absorb something like bromine on it. And this is one of the, I would say, almost historical papers on that one, where when you put more bromine on it, you start here on the top, when it's pure, the tungsten, and when you to bromine on it, you don't see the tungsten underneath. So the more bromine, the less tungsten there is, because you only look at the top layer. So it's either tungsten or bromine, and there's nothing else. And that gives you a straight line, and here will be full coverage. And that is typical, but also unique for a surface analysis. If you have another technique like OJ, XPS, you get an average over, say, 10 atomic layers or more. So if you do that, you will never get a linear relationship. So it's easy to quantify if you just look at the outermost layer. It just simplifies things. You don't have to worry about how many atoms there are in this second layer. How does the analyzer work? It's a double toroidal analyzer, as it's called. You come in with ions from the top, all kinds of optics. They scatter from the surface. If they come back between these these electrodes here, they are deflected, first to the left, then to the right, you go up, and you get the fast ones move further out, and so there is at the end an image in energy. And that is essential, so it means I do not have to scan through all the way through the spectrum, and while scanning I bombard and kill the surface. So I can use in parallel, get a major fraction of the spectrum. At the same time, these ions, they scatter back in a cone. So they come in and they scatter back in the full cone, the 2 pi. So you have a very large acceptance angle, you do parallel energy detection, and because of that, typically you have, say, a factor of 3,000 higher sensitivity than other instruments in the field, at least for a given mass resolution. It's also important to realize the ion comes in, it scatters, it is on the way to the detector, and at that moment that it scatters, the surface is still undisturbed. Afterwards, so after the collision, because you transfer momentum, some damage may happen. But the ion has already the information of the undisturbed phase. So if you never come back to that place, you know what is in the outermost layer before any damage. Just to get some numbers, here you see some sensitivities for light elements. Lithium, you are not so good, your sensitivity is not fantastic. Say you go, say, lithium oxide around a percent, a few percent. Fluorine, chlorine, you get better. And once you get to the heavier elements, finally you end up with sensitivities of the order of 10⁻⁵, but of the outermost atomic layer. So if you compare that to other techniques where you average, say, maybe have a sensitivity of 10⁻³ if you have a very good instrument with XPS or OJ, but that is averaged, integrated over many atomic layers, and now you can do, say, a gold or a platinum 10⁻⁵ of 1 atomic layer. That means even in catalysis, in supported catalyst, you have the sensitivity to, say, for any commercial catalyst to see what is in the outermost atomic layer, even if it's very low loading. I don't want to go to the next one.
Use the computer.
Well, if not, I'll do it this way. Okay. This is an old example, but it does illustrate what the impact of this development is. This is a catalyst of palladium platinum nanoparticles on a carbon support. So you have a very rough surface of about, say, 1,000 or more square meters per gram. So it's not flat, it's a real catalyst. And there is a little bit of platinum and palladium, too little to see, certainly in those days, with any, say, XPS machine. You couldn't even see that it was there. And in the old days, that's the left here, we were very excited. We could see the palladium and we could see the platinum peak. However, you needed so many ions that this is 10,000 nanocoulomb. That means a lot of ions, so basically you kill the sample at the moment you get that spectrum. The modern way is here on the right. You see you need only 5 instead of 10,000, and you get fantastic, well-resolved peaks and good statistics. And even, I always tell these arrows, yes, that background was made up by myself, because we can see promoters and all kinds of other things on these catalysts. We have the sensitivity to do that, but we are not allowed to show that. So I just made up my own background there. There is one tool that is important, and that is this, what I call an oxygen atom source. And that is this is for cleaning your samples before analysis. So if you have an oxide, what you can do is make an oxygen plasma and then filter them so that only the oxygen atoms, not the ions, not the electrons, only the neutral particles get through, and they even only have thermal energy. That means that if I have a sample that got transported from some other place around the world, sent to you and got dirty by whatever pollution, you have hydrocarbons, and what you do is you treat it, say, about 5 minutes, and you eat away this dirt, and you get your clean oxide afterwards. And it's a very powerful tool to be able, because if you look at the outer layer, it's nice that it's a well-defined layer. Depth profiling, there are 2 possibilities. There is one that you do the analysis and you can sputter at the same time and do a depth profile. There's another way to do it, and that's called static LEIS. And I'll just show you the principle. I discussed up to now the ion scattering from the top layer, but of course many of them will go in, get neutralized, boom, 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 scatter, may come back to the surface. But if they are still neutrals, I cannot see them. I have to go through this special analyzer to be deflected. Now, the trick is that many elements, certainly at a little higher energies, have the probability that if it, before it leaves, say for instance helium hits an oxygen atom, and there's a probability it gets reionized. And because of that, you can get information of the deeper layers. So if you look at the right, you see, first of all, an energy spectrum. Now it's on its side. The surface peak here of zirconium, but you get a tail, this background, and that is the in-depth distribution of zirconium for about, say, a couple of nanometers. And that's, especially for microelectronics, nowadays a very important tool. This is real life. Here you grow with a technique like atomic layer deposition, cycle by cycle. You put more zirconium on it, and you see that in the beginning you have a silicon peak and the oxygen. You grow the zirconia, small peak, more zirconia. After each cycle, zirconia goes up, silicon goes down, and again, if you look at the right, it is this straight line. It's either zirconia or silica, so you understand that's the quantification you know. But you see also that, first of all, here this red one, you miss still about 3%, and it is a quantitative technique, so you know, there is still pinholes in my layer, and yes, there is also a little bit of silicon still to be seen. That is the kind of accuracy you get. On the other hand, there is not only just the peak, you see this background is stale at the low energy side, and that gives you a depth profile, and here I've indicated the scale. So for instance, for the black curve after 100 cycles, you see I have more or less a complete monolayer, and there is already at the same time places where it is 3 nanometer thick, the layer, and at other places it is less. So you get the distribution, and we know how to evaluate that. So, summary, LEIS, you have certain sensitivity for one monolayer. You also have a sensitivity in depth with depth resolution, and how that compares with the other techniques. Now I come to some real applications. So, first of all, well, things like imaging, surface segregation, and a few others. And so here you see a picture of a microelectronic structure. The field of view is not fantastic nowadays. The typical lateral resolution with the new ion sources you can get is about 10 microns. One process that you, when you do ion scattering, you become aware of that almost any material in the world is dirty, so to say. There are always materials that either from the atmosphere absorb and do things, or they come from below. In this case, this is an ABS polymer, and you see that, well, it is ABS, so it's acrylonitrile, butadiene, styrene, mainly carbon, nitrogen. You see a lot of other things, all these elements. These are additives to these polymers, and they come to the surface and they control the surface. Of course you can say, well, I don't care, I want to know is it ABS, but if you do any chemistry or any adhesion or other process with a polymer, it's very important that you know about what is really there and what controls the surface. Another thing, anti-wetting. If you take polymers with fluorine in it, the fluorine always likes to get to the outer surface, which is responsible for anti-wetting. And here we plot, for instance, the surface energy, which tells you how strong the bonding is, at the surface, against the number of fluorine atoms that we determine. And so we see that when we have more fluorine atoms, the surface energy is lower, and so it is more anti-wetting. It's very easy to do a quantitative number of how many fluorine atoms are there in the top outermost atomic layer. If you would do that with any other surface technique, you don't get any straight line, because you also see the second, the third, or the 20th atomic layer, and there is no correlation between these two. Evaporating, making light-emitting diodes, polymer light-emitting diodes. If you want to make an electrical contact, you evaporate some barium on a polymer called PPV, and you try to get a sharp interface, because the sharper the interface, the more light comes out of your device. But in reality, you see that if you evaporate barium, that this cartoon is more real than the top one. And how do you see it? Well, this is, the blue is supposed to be the peak if the barium was just in the top layer, a nice Gaussian-shaped peak. And the asymmetry tells you that in reality, the barium immediately diffused down to about 7 nanometers. So unless you are clever, play tricks, you cannot avoid that, and you lose a lot of sensitivity. So in our lab, we did all kind of, we did this in situ while making these layers. We could immediately transfer it to the LEIS and see how that works. Surface modification, I took the example again of a polymer, but it's for all kinds of polymers. What you do is you oxidize in this case, high density polyethylene. You oxidize it with an atom source or a plasma, and you functionalize it in the top. And then, well, the background is that many years ago I was responsible at Philips Electronics for the compact disc and everything related. And we try to make, you have a polymer and you try to put a metal like aluminum, silver or whatever on it, and you want it should adhere. We try to be clever, so we said, well, let's make many discs, and next week we evaporate the metal on top. It did not stick anymore. After 1 week, everything was gone. Well, this is basically the type of reason why that is. If you plot the oxygen signal of that against time and say this is 5 minutes and this is about 2 days, then you see these functional groups are there, but in real time they turn around and are not available for chemistry anymore. If you do another technique which looks deeper, nothing happens so much because they are still within the information depth, so you don't see anything happen. And so it's very important that you look, follow it in the outer layer, and in that way we could make better contact, better adhesion layers. Nanoparticles. Of course, transmission electron microscopy is one of the key techniques to look at structures. However, when things get small, it's not always when you get below 2 nanometers, and when you have a real catalyst with lots of structures and heavy elements, it may be very difficult to see any nanostructure. So we helped work together with companies like Johnson & Matthey and Toyota to get better particles. And how does that work? Well, if you have a surface, a rough surface with nanoclusters, in ion scattering you only see the top part of such a nanocluster. So if you know the total loading, how much platinum there is in total, and you know how much I see, then you can do an average, a surface and a volume. The ratio gives basically an average of the diameter of these particles. And that's in fact all there is to it. So we can determine the size of these particles, especially when they get small, because then there is more surface, so it's easier to measure. So once they get below 10 nanometers, and in this particular case it's the 3-way catalyst that you have in your car, a typical size is 1.6 nanometers of these particles. And of course, if you want value for your money, it's very important to measure that, because, you don't care about all the other platinum which is not at the surface and not available for catalysis. You care about these. Core shell particles, these are special sensors where there should be, you need the tin which is in the core of these core shell particles, but you don't want these, if you have many tin particles, they react together and they would form one big block of tin, so not much surface area. So the trick is that you add some silica around it. But if you make a full layer, well, then the chemistry with tin is gone. So it doesn't work either. So the trick is to do, how do you make a layer which, so they don't stick together, but at the same time there's open space. And so here, this ion scattering spectrum where you have both silica and tin, that is this kind of structure, and that's the one that you need for this kind of sensor. Mixed oxides, and I'll take the example of spinels, things with the structure of AB204, and this is well, nowadays we can do much better with, because the machine is much better. It's an old spectrum, but it tells you that you see the oxygen peak, the aluminum peak. Oops, no zinc. Where's the zinc? Well, it's there. You see there is a background. But the zinc is just in the second atomic layer. That means it's not available for chemistry. We do not see it as a peak. We only see it as the tail in the deeper layers. And that is basically what you see here on the right. You have if you have a single crystal, we basically only look at the outer layer. Now you may say, well, do you do catalysis with single crystals? No, we have powders. We have high area powders. But nature only likes to have the surface planes that are very stable. And these are the planes where zinc is in the sublayer and aluminum oxide is in the top layer. So if you want to understand catalysis on spinels, you don't want to get an average of 2 or more layers. You only get a correlation if you can look at the outermost layer. Oops. So for instance, in this particular case, we have cobalt spinels with cobalt in it. 1 cobalt, 2 cobalt, 3 cobalt. And we correlate catalytic activity with what we see. And you see that if you have 1 cobalt, this one, well, and practically no signal, no cobalt signal, no sensitivity for catalysis. Here, fantastic. There, it's the same. Why? In this one, only the atoms in red are in the octahedral site. They are at the outer surface. The other ones are just below, in the tetrahedral site. That is why here you don't only see the alumina, no cobalt. Here you see both of them. And there, well, you cannot see more. The third one is again in this third layer. So you have a direct correlation between catalysis and what you see, which you would not have with any other technique. Typical thing, same happens with perovskites, yttrium-stabilized zirconia. You generally, well, you would hope to get, if you have Y as Z, you hope to have yttria or zirconia in the outermost layer. There's none. You see no peak there. That means there is not a single atom in the top layer. What is there? Well, anything you want. Calcium, hafnium, sodium, silicon, fluorine, all kind of impurities. And then you think, well, they got a dirty sample. Well, true. But it is the highest purity of this material at that moment. That means that as soon as you use these materials, these are ceramics for fuel cell, operating at, say, 800 degrees C, all these impurities move like crazy, form a monolayer, and then it stops. It gains energy by covering the surface with dirt. And that means there is no yttria and zirconia, and you should be clever to get that away. You can also do O16, O18 exchange, and if we have cleaned with sputtering the surface, we can get a clean surface, and then we can get the isotopic exchange. But as soon as we heat again, the calcium moves to the surface, covers it, and then you see I cannot exchange it anymore because the elements I need, yttria, zirconia, are not available in the outermost atomic layer. So this is more on how to do that. Atomic layer deposition. I showed you already a little bit before. It is very important. How do I do cycle by cycle grow, that it goes layer by layer by layer, so that it is a very homogeneous layers, a uniform thickness. However, if it nucleates at one place, after cycles it starts at some place, it goes out. But there are other places that are still uncovered. And it may take many, many cycles. Sometimes it takes 200 cycles before that layer is closed. And I showed you, it's an older series, I showed you, yes, there are a few cases where it does go layer by layer the way you want, and so but most of them are three-dimensional layers. That means it nucleates, gets bigger and bigger, and at other places there's still nothing. And so it is very important to be able to look at the beginning. So after a few hundred cycles, you cannot change that there was some mountains. You just cover them a little bit. But the initial growth is important. That decides on how uniform your layer is. One example here for microelectronics, when you grow layers like titanium nitride, in this case it's supposed to be 3 nanometers of titanium nitride on a silicon wafer. We do the depths, the non-destructive depths information, and when you see here, you see there is, if it was ideal, like this black curve here, that is when it's a well-defined layer. In practice, it's not a well-defined layer. There is at the surface, it's titanium oxide, it got oxidized. That is why it's not. You see in blue, the real life, it is lower than the simulation. And here you see that it also diffused in, and so you have to change the parameters in the ALD growth if you want to get a well-defined layer. So, initial growth, poisoning, pinholes. So for ALD, this is a very strong thing. Let me slowly get to a summary. What I've been trying to tell you is that, oops, okay, you see that we have this, we can look at the outermost atomic layer and in depth. We can look at surface segregation, anti-wetting, and all these things. Teach you that the outer surface is very often different from what you think. And so if you want to understand chemistry or adhesion or somewhere processes that are surface related, it's good to know what's at a real surface. And I illustrated that with oxides, SOFC membranes, and ALD growths. And of course there are these real academic applications, but in practice I've been running an application lab since the mid-90s, and we do all kinds of other things. So candy wrappers, these starfighter related things, bone tissues, dental implants with dentists in Holland, aging of carpeting, floor wax, diapers, all kinds of things. And we take advantage of the fact that with ion scattering you can look both at the top layer and in depth, and you try to be a material scientist to make that properties. Thank you very much.
So any questions for Professor Brongersma? Okay, thank you again. So let me give you some housekeeping. My laboratory,